Hi, and welcome back to this next video on training neural nets, right? So in the previous video, we introduced the backpropagation algorithm, and one of the previous videos before it, we also looked at feed-forward neural nets, and in particular, the fully connected ones. And in this video, we'll try to combine the two and just go over how backpropagation will work for fully connected feed-forward neural nets and derive some easy formulas towards the end of it, towards the end of the video. So just to remind ourselves what was the notation we introduced early on. And we have one of these fully connected feed-forward neural nets. One convenient representation was that each of these layers between two layers of neurons, all the weights on those edges are represented by matrices. So if you look at the ith hidden layer, for instance, the first one here in the middle, then the weights that are coming in are represented by the matrix W1, and all the biases are represented by a vector B1. And then we also assume that all the neurons in the same layer, all the non-biased neurons, they use the same activation function phi. So this was all covered in one of the previous videos, so watch it again if you're not comfortable with it. Then what we saw was that the way to evaluate this feed-forward neural net is that if we think of the input as a feature vector x, this time placed as a row vector, that's important. So a row vector with x1 and x2 as the input values. Then you first multiply it from the left onto the first weight matrix, W1. And here W1 is the matrix, has a column per neuron in the output layer, or the middle layer here, and a row for each of the neurons that are at the layer below it. Okay, so you compute this product, it gives you a new row vector with an entry per non-biased neuron in this hidden layer here in layer 1. And then you add up the bias vector B1, which is again a row vector with one entry for each of these neurons. And so this gives you all the signals that comes into all these neurons, and then you apply the activation function entry-wise to this vector that you get here. All right, so watch the previous videos again if you don't remember this notation. Okay, so once you have, this is the value of the non-biased neurons in this hidden layer here, you just continue upwards through the network. So this is a vector again, a row vector with all the outputs of these neurons, and then you multiply it onto from the left onto the second weight matrix. And this gives you one entry for each of the output neurons here. You add the bias. This time it's just a vector with a single entry. You add the bias here and you apply the second activation function, right? So this is how we evaluate these fully connected feed-forward neural nets. In particular, we can write it as this nested evaluation, where in the middle here again, right, we have our feature vector x, we multiply it onto the first weight matrix from the left, we add the first bias vector, we apply the first activation function. So it's a new vector that is then fed into the second layer of the network, where we apply it again to the second weight matrix from the left, we add the second bias vector, and we apply the second activation function. And then we keep going until we reach the very top. We get the activation function, or the output from the layer just below the output. We apply it from the left to the last weight matrix. We add the last bias vector, and we apply the last activation function. Right? So this is how we, in general, have these fully connected feed-forward neural nets. Okay. Now, so if we want to use this backpropagation framework, it makes sense to write down this computation graph that we also defined in the previous video. So here we're going to define a vectorized computation graph just to keep things simple, at least notation-wise, and also if you wanted to implement it, it's much easier if you can do it with vectorized notation. So here's really a computation graph that kind of corresponds to what's happening over here. So what do we have, right? So we have nodes in this graph that compute a product between a row vector and a matrix B. So an AB product here. And what happens here is that, well, we first take the input feature vector x, multiply it onto the left, onto the first weight matrix, right? This is basically what we were doing before. And then we add the first bias row vector to it. Then the output of this is a vector, again, a row vector. We apply the first activation function. Now we've evaluated all the values of the non-biased neurons in the middle hidden layer. Then we multiply it as a vector onto the left to W2. We add the second bias vector and we apply the last activation function, right? So this is really a vectorized computation graph describing the evaluation of this feed-forward neural net over here. Okay, so what we'd like to do is we'd like to compute gradients. If we want to compute the gradient of the output, well, eventually we would actually build a loss function on top of it. But this is just more of the same. So we'll just ignore it for now to keep things a little simple. Just focus on these A times B type of nodes and these activation function type of nodes and see how to deal with them. And the basic idea was that eventually we would like to compute the partial derivatives of this function with respect to both the W1, W2, B1, and B2, right? Because these are the parameters that we're going to do gradient descent on. And we want to use this forward plus backpropagation framework that we saw in the previous video. Okay. So of course, right, we could just finish now if we just say, okay, we can take this vectorized computation graph, turn it into a normal computation graph where everything is just single scalars that are all the variables. I can inflate this W1 into a whole bunch of single variables, one for each of the entries in W1. And of course, this would work. We could just run through the steps that we saw in the previous video. But this is a little tedious. And so if we can find a more convenient matrix vector notation, perhaps for doing it on this vectorized computation graph, that will be easier also to implement. It'll also be faster in practice. So we'll try to see if we can at least get some rules for how to compute gradients for such a beast like this one. Okay, so we'll try to follow the same template approach, and then when things kind of break down, we'll see how to fix them. So we give the name, all the internal nodes a name, like they have in before. And so the output here is F. We have an E node, a D node, a C node, B node, and an A node. And then we do the forward pass, which means that we're going to evaluate the neural net at the current set of parameters, right? So let's see, right? So let's try to give it some input parameters that would make sense for such a neural net and see what happens, right? So here's an example, right? So of course the shapes have to make sense. So X here, the two inputs next. So this is a row vector of 2 entries. W1, if you remember, it has a row per input neuron, and it has a column per output neuron here. So it has to be a 2x2 matrix, which it is here. And so like the second column here, the weights on the edges entering this second neuron in this hidden layer. So this would be the weight on this edge down here and the weight on this edge here. Okay, we have the sum operation here that takes as input this bias vector here. It's a row vector with 1 entry for each of them. And I guess also we need to have a second weight matrix that goes between the hidden layer and the output layer. So it has only 1 output neuron, so it has 1 column and must have 2 rows like it has here. So this is a valid set of parameters, setting of parameters for this neural net here. Okay, so what happens in the forward pass, right, is that we forward these values up the edges, and then we just go through the computation one step at a time and evaluate the nodes, right? So we first compute this product AB, and if you see what happens here, right, the first entry is going to be the inner product between the first column of the matrix here and this row vector A. So it's 2 times 2 plus 1 times 0, that's just 4. And the second entry is, well, the inner product between the second column and this vector here. So 2 times 1 plus 1 times 1 is 3. Okay. We had the summation here, very easy. We just add the 2 vectors. There's an activation function here. Maybe let's just, for simplicity, say, well, maybe this activation function is the one that squares all the entries. Recall, right, these activation functions, they're just applied to single entries of a vector, right? So we just need to square the input entries here, so 5 squares and 4 squares. And now we have this. The D node is computing a product here between a row vector and a column vector. It's just the number, 25 times 1 minus 16 times 1. So that gives us a 9. Now the E node is going to add minus 2 with 9. So we're going to get 7 here. And okay, the output node has an activation too. Maybe let's say this is a regression problem that the output is just identity. So then we're going to output 7. All right, so this is just evaluating the neural net. This is all stuff we've seen before. Now, of course, the tricky part is the backwards pass. So let's just get started. We had this rule that kind of, if we want to put a gradient on all the edges, we should just start by putting 1 on the output edge, the final output edge. And then we just go backwards down through this network, the computation graph. And in each of the nodes, right, we use the chain rule. And well, I guess, so let's start by E here. So we want to compute what's on the edge E here. So I guess we can say the partial derivative of f with respect to E, I guess, is the same. So we can say, what is the f expression? The f is the identity function. So it's actually, f is just the function E. So we're looking for the partial derivative of E with respect to E. That's just 1. So let's just put a 1 on this edge. Okay. Now we want to compute the partial derivative of f with respect to d using the chain rule. We look at the node just above it here. That's the e node. So it's the partial derivative of f with respect to e times the partial derivative of e with respect to d. We already computed the partial derivative of f with respect to e. That was just 1. This is what's written on the edge up here. So we have a 1. And now what is the e function? Well, it's exactly, in this case here, right, it's the value d plus the value b2. So this is an important thing, is this is not a square, it's the second bias vector. So it's just a b2, there's only one entry in it. It's just b2, there's nothing squared here. So it's the sum of d plus b2, and we have to compute the partial derivative of this with respect to d. That is just 1, so 1 times 1 is 1. So we have another 1 here. Okay. We can also do the partial derivative of f with respect to b2. So chain rule, it's the partial derivative of f with respect to e. So we take the node above it here, times the partial derivative of e with respect to b2. We already have this value here, the partial derivative of f with respect to e, that's 1. And the sum here, d plus b2 with respect to b2, that's just 1. So we get a 1 on this edge too. Okay, so far so good. Everything has just been the same as before. Okay, let's try to move down. Right now we want to compute the partial derivative of f with respect to c. So what happens here, right? So it's the partial derivative of f with respect to d using this chain rule times the partial derivative of d with respect to c. So here we have our 1, right? That's what's on the edge, the out edge. That was easy. The partial derivative of d with respect to c. So now the issue is that c here is not a scalar, right? C is actually a vector. What's being output here is a whole vector. So how do we proceed when this is not a scalar, right? So does this make sense what we're doing here? And the thing is that this is actually still correct, this chain rule application here, only that we should not think of this as a single numeric value. Instead, it's going to be the matrix of derivatives that we saw before, which is also called the Jacobian. Okay, so it's basically just we think of d as a function of the vector c. So and this is a function of 2 outputs, right? A c1 and a c2. And then we just have to compute this matrix of derivatives. Okay, so maybe let's just remind ourselves what such a matrix of derivatives is. So in general, a matrix of derivatives or Jacobian is if I have a function L that actually outputs k values, so it's really k functions, right? So it outputs a vector of k functions. It's a function that takes d input variables, x1 to xd. So then this is a function from rd to rk. And if we assume that each of these functions are differentiable, then this Jacobian or matrix of derivatives is the matrix that has, well, it has 1 row for each of these output functions, right? So it has k rows and has 1 column for each of the variables. And the ith row and the jth column has the partial derivative of the ith output with respect to the jth variable. Right, so this is just what this matrix of derivatives is. So the first row just has the first output function, and it contains all the partial derivatives of the first output function, and so on. Okay. So if we go back here, and the rule says that now we should just compute here, we should plug in the gradient, now this matrix of derivatives, sorry. So the matrix of derivatives, we have to figure out, so what is this function d as a function of c? So really, right, if we think about it, well, d is outputting 1 value. So the matrix of derivatives must have only 1 row. With only 1 output value. Okay. Now, how many input variables are there if it's a function of c? Well, c actually is the vector c1, c2. So there are 2 input variables. There must be 2 columns, and each of the 2 columns contain the partial derivative with either respect to the first variable in c or the second variable in c. Okay, so the function being computed here is the a times b function. And so what is this function, right? So the function is computing the product between c and w2. So again, there's no square here, it's just w2. So it computes this product. And if we expand out, what is this product between c and w2? Well, you take the first entry of c1 multiplied on with the first entry of w2. So it's c1 times w1. In the second w matrix, it's the first entry. The c2 is the second entry in the c times the second entry in the w2 vector down here. Okay, so that is the function that's being computed. So it's only one function. This is one we have in both columns, and then we take the 2 different partial derivatives. And what we see here is that this is just when we took partial derivative with respect to c1, all we get is the first entry of w2. So this is the first entry of w2. There's no square here. It's just the first entry of w2. Similarly, if we take the partial derivative with respect to C2, we get the second entry of the W2 matrix here, or vector. So when we just have to evaluate it at the current set of values, so what we get here is like a 1 and a -1 as a row vector. Okay, so back to the chain rule, right? So we had to take what we got here in the output, that's the 1, there's the entry that's just the 1, and we have to multiply it with the 1 - 1 vector, and this gives us just the 1 - 1. So this is the partial derivative of f with respect to c. Okay, now let's continue down, right? So now we go one step further down. We want to compute the partial derivative of f with respect to b. Using the chain rule, we should take the partial derivative of f with respect to c. That is this row vector here. So that's what we get here. And now we need to compute the partial derivative of c with respect to b. Okay, so c now is a function that has two outputs, right? C1 and C2. And it's a function of two outputs from b. So there are two variables, b1 and b2. So it's going to have two rows. And the first row is going to look at the partial derivative of the first output, C1, as a function of either B1 and B, with respect to either B1 and B2. And the second row, you look at the second output of the C function. So that's the C2. And you think of it as you take partial derivative with respect to B1 and B2. So this is the matrix derivatives that we have to compute. Okay. So what are these entries? We need to figure out what are these partial derivatives of CI with respect to BJ. So the partial derivative of CI with respect to BJ, we look at what is CI, right? So what is the C function doing? It's squaring each of the individual entries, right? So it's squaring, the first entry is going to be the first entry of B squared. So CI is BI squared, and we have to look at the partial derivative with respect to BJ. Now, what you see here is that, well, if I is not equal to j, then this is just 0 because bj does not appear in the numerator. And otherwise, here it's just going to be 2bi. So really, this matrix of derivatives is going to be the diagonal matrix that on the first diagonal entry, it contains 2 times b1, and on the second diagonal entry, it contains 2 times b2. Off diagonal is 0. Okay. And now we just plug in from the forward pass, we know what B is. So here we plug in the 5 in place of B1, we plug in the 4 in place of B2, and we get the matrix with 10 and 8 on the diagonal. So which means that this partial derivative of f with respect to B is going to be 1 - 1 times this matrix 10 and 8 on the diagonals. And what happens here is that basically you just multiply 10 onto 1, you multiply 8 onto -1, and you get the row vector 10, -8. So this is the next step here. Okay. And we can proceed down. So here we have a sum operation. So chain rule again, partial derivative f with respect to b. And now let's do it with respect to b1 out here. So now the partial derivative of b as a function of b1. So b as a function of b1. What do we have here? Like, so b now, if we think about it, right, it's a function that has two outputs. And as a function of b1, it also has two inputs, the two input values in b1. And the function that it computes, the first output function, right, the first value here is the first entry of the a input plus the first entry of this b1 vector. All right, so then we take partial derivative with respect to the two different variables, the first entry of b1 and the second entry of b1. And, you know, the second output is the second entry of a plus the second entry of b1. So this is the matrix that we have to compute partial derivatives of. And if we look at it, we see, right, well, the first expression here, that's going to give us a 1. The second expression, the second entry of b1 does not appear. So this is going to be 0. Similarly, down here in this corner, the first entry of b1 does not appear. So this is going to be 0. And down here, it's going to be 1. So this is just the identity matrix. So, which means we compute the partial derivative of f with respect to b1 is just the row vector 10, -8 that we got from above, times the identity matrix, giving us 10, -8. Okay. We move on. Now we want to compute the partial derivative with respect to a. So we use the chain rule and get partial derivative of f with respect to b times the partial derivative of b with respect to a. And we already know the first part here, 10, -8. Now we have to compute this matrix of derivatives when b is thought of as a function of a. Now, okay, so b is a function of a. Again, we already know what the b function was. The first entry is a1 plus the first entry of b1, so on and so forth. And I guess here, it's easy to see we get 1 on the diagonals and we get 0 off the diagonals. So it's the identity matrix again. And we just get 10, -8. Last two steps, we now just need to compute, now we're going to compute these partial derivatives. Let's do the one with respect to x. Partial derivative of f with respect to a times the partial derivative of a with respect to x by the chain rule. We know this partial derivative is 10 comma minus 8. So now we're going to need to compute the matrix of derivatives of a as a function of x. So a as a function of x, what do we have here? Well, a has two outputs, right? So the first output is the inner product between the first column of W1 and x. So this is what we have here, right? So it's basically what we have written here is the inner product between the first column of W1 and x, right? So this is what we have both places. The second entry is the inner product between the second column of W1 and x. And now we need to take, well, there are two variables, right? There's the x1 variable and the x2 variables. We need to take partial derivative with respect to both of them. And if we look at this expression, right, we'll see the first one here, we'll just get the W1, the 1,1 entry of W1. Over here, we get the entry 2,1. Down here, we get the entry 1,2. And down here, we get the entry 2,2. So it's going to look like this. And, well, if we look at it, what you see here is that this is the matrix that as its first column, it has the first row of W1, and the second column is the second row of W1. So this is actually just W1 transposed. Okay. So this matrix of derivatives is W1 transposed. So we plug in W1 transposed up here. So that's the 2, 0, 1, 1 matrix. We carry out the product between these two. So the first entry is 2 times 10 plus 1 times minus 8. That's 12. The second entry is 0 times 10 plus 1 times minus 8. So it's minus 8. So we're down here. Okay. And let's continue with partial derivative of f with respect to W1. So again, the rule says partial derivative of f with respect to a. We already know this. Now, partial derivative of a with respect to W1. Now, a is a function with two outputs. And W1 is, so I guess the function here, it has 4 variables, but it's not really placed in a vector or anything. So it's a little unclear what are we supposed to put here as the matrix of derivatives. And so what happens here when this is a matrix? Right? So we have to think a little bit. Instead of this is not just a vector of entries, it's a matrix. So what do we do? Now, the short answer is that what you actually do is that you can think of taking this W1 and just flattening it out into a vector. So you can kind of just take the first row and place it first, and then take the second row and place it afterwards. Now, if we start by flattening it, then we can at least compute the partial derivative of f with respect to this flattened vector. We know how to do that, right? Because this is just like the things we've already been doing. So we can just try to do it the same way. So using the chain rule, now we have this 10, minus 8 from above. And now we need to compute the matrix of derivatives of the expression a as a function of this flattened vector W1. So what is it then? Well, we already know, right, that the a function has two outputs, right? One of them is the inner product between the first column of W1 and x, and the second is the inner product between the second column of W1 and x, right? So we can just write it out as an expression of these individual variables like we did before, right? This is just the inner product between the first column of W1 and x. And now there are 4 variables in this flattened vector here, in this flattened W1. One of them is W11, one of them is W12, the second one is W21 and W22. So we just compute all these partial derivatives. And what do we see up here in this top corner, right? We get, well, with respect to W11, we just get x1 up here. In the second column, we're computing partial derivative with respect to W12. So that's the second entry of this top right corner of W1. And we can see that, well, this is multiplied onto x1 in the second output, right? So it's the second output of A is the inner product between the second column and x1. So it's going to appear down here at the bottom. We're going to get an x1. When we take partial derivative with respect to W21, so the entry down here, W21 in the lower left corner, you can see that this is part of the first output. It's the first output is the inner product between the first column and x, and it's multiplied onto x2. So what we end up with is this matrix here, the matrix of derivatives. So we can, using the chain rule, we can just multiply these two together and see, well, x1 here, that's 2, and x2 is 1. So we can plug those in. We can compute the product here. So this becomes now a vector of 4 entries. And if you just compute them right, you will get exactly this vector here, 20, minus 16, 10, minus 8. I guess you can see that the first value is the 2 times 10. The second value is 2 times minus 8. And the second value is 1 time. The third value is, product here is 1 times 10, and the last one is 1 times minus 8. So you get this 20, minus 16, 10, minus 8. Okay. So this is if we flatten W1. And now the rule is just, you can just deflatten it again by doing the reverse transformation, right? What we did when we flattened it was we took the first row and placed it first, and then the second row and placed it afterwards. So we can just deflatten it. So this is the first row, 20, minus 16, and this is the second row, so 10, minus 8. So that's just the rule. You can just, we know how to do things when we're taking partial derivative with respect to a row vector. When we have multiple variables placed in a row vector, so we can always flatten it to a row vector, compute with the matrix derivative what is these gradients, and then you can deflatten it back. Okay, so this gives us this matrix here, and well, for W2 is not really a row vector. So, but what we can do is we can, well, D has one output, and as a function of W2, it has one output, the 2 inputs. These are the 2 variables in W2. And well, all we need to do is to basically do this flattening again, because this is now a column vector. So if we flatten the column vector into a row vector and think of it as and just do the same rules that we already did, and then afterwards we just deflatten it again, then we're going to get a column vector instead. Okay. So this is just doing the same steps with actually flattening it, because this is not really a row vector. All these steps that we did, they really work best if it's a row vector, but everything is just flattening and unflattening, then things work. Okay. So I guess the point is that this is very tedious, but you can do it. But I think the interesting case is to just look at, here's a summary, like what were the main types of nodes that we have, right? And I think the one that caused the most headaches were these A times B nodes, right? Those are the most tricky ones that we had. And I'll just give you here the rules to remember when you have such a vectorized computation graph. As soon as you have those rules, then things are easier to do. You just have to memorize a couple of rules, and then things are fine. So if I have a node like this, well, the partial derivative of f with respect to a, well, you always need to take the partial derivative, the one that you have above here, the partial derivative of f with respect to c. So you always put that one here. And then if this is an AB node, and you're looking at partial derivative with respect to a, the rule is you should multiply with b transposed. Okay, so you just multiply with b transposed from the right, and that gives you the result. So this is what we can do here. This is what we did before. If we transpose this matrix and multiply it onto 10, minus 8, you're going to get 12, minus 8. So that's the one rule to remember. If we're looking with respect to a, we just take b transpose and multiply it onto what the gradient that we have from above. Okay. Now, also, if we do, if you want to do the partial derivative f with respect to the b matrix down here, now the rule to remember is that you should take what you have up here in the C node, and so this is a vector, and then you should place copies of it down through, stack them on top of each other in the matrix, and you should multiply each copy by each of the values in A. So you basically take A1 and multiply with this gradient and place it first, then you take A2 and multiply with this row vector and place it second. So this is what we got before also. We take the A1, that's a 2, we multiply it onto the 10, minus 8, we place it as a row vector. We take the second entry, multiply it onto it, and place it as a row vector. And so that's the two rules to remember if we have the AB nodes, and then you can continue. Okay. So with these rules, it's not too tricky. When we had the summation node, this was the easy one, basically because this becomes the identity matrix if we looked at the partial derivative of C with respect to A or C with respect to B, you just get the identity matrix. So basically just copy this 10, minus 8. This is what you do in both places. Whenever you have a plus, you just copy it. Very easy. Okay. Activation functions. the rule to remember here with activation function, they applied entry-wise. And if we want to do the partial derivative of f with respect to b, I take the one I have up here, the partial derivative of f with respect to c. And now this matrix of derivatives for the partial derivative of c with respect to b, or the matrix of derivatives that we get here, all you have to do is you have to compute the derivative of the activation function and apply it to the b vector on the diagonal. So you kind of value, you apply it to b1 on the first diagonal entry and so on downwards. So that's all you need to remember. And maybe want to just to see an example here. Let's say we have a kind of crazy activation function like e to the x squared. Now, well, you have to compute what is the expression for the derivative of e to the x squared. By the chain rule, it's e to the x squared times 2x. And if we want to apply this over here, then what is this matrix, right? So we have to plug in b1, that's a 4. We have to plug it into this expression. So we get e to the 16 times 8. And the second diagonal entry, we plug in 3. So we get e to the 9 times 6. So this is the matrix that we have to multiply on to 10, minus 8. And if we do that, we get something like this, like 80, e to the 16 minus 48, e to the 9. Okay, so that's the rule to remember here. And, this is an exercise to prove, so you can practice and just sit down and actually prove this by going over the definition of the matrix of derivatives. Okay, so actually with these rules, we can actually implement stochastic gradient descent when we have this pointwise loss function, right? So the pointwise loss function here, inside the loss function, we have the evaluation of the output of the neural net when you have the current setting of weights and biases. And now we down here, just to remember when we're computing these gradients throughout the execution, right, we're computing all the partial derivatives with respect to all these variables that are part of the neural net, all the weights, all the biases. Then we just have to remember to on top of it just include the loss function in the in the computation graph that we just saw, right? So we also saw in the previous video how to do it. It's just important that it's the loss function we're computing gradients of with respect to the variables, right? Because it's the loss function we want to minimize. So just remember to include that in the computation graph. Okay. So we went through all these computations. It was very tedious. You could do it. I think it's a good exercise to try it out at least once, just to understand what's happening, right? So see that you can actually carry out these steps, and maybe also try it at least once to just appreciate that you can automate this process, because it is really tedious to do it by hand. Right, and this is what is implemented in libraries such as Pytorch, which is a popular open source free available library for doing so. And here's just, if you want to use this library, how could you actually do it? So here's a simple example where at the top we just define all these input variables, right? We define x, we define w as this matrix here, we define w2 as this column the matrix with a single column, and b1 and b2. And then all you have to implement, and that's the really nice thing, is you just have to implement the forward pass that describes the computation graph, right? So the forward pass is, well, the A node computes x times w1, the B node sums a and b1, the C node squares all the entries of the input b, the D node, this is entry-wise squaring in Pytorch and NumPy. D computes the product of C and W2, E computes the sum of D and B2, and F just outputs E. You can tell, if you want to, you can just tell Pytorch to actually store all these intermediate gradients so that you can see them if you want to. And then the only thing you have to do is just call this f.backward. If you make this call f.backwards, then on these variables here, all the intermediate variables that you have up here, and also the input variables, it has a field called grad, and this just tells you what is the gradient of f with respect to all of these parameters here. So if you run this, it actually does all the stuff that we did up here. So we can try to see. Partial derivative of f with respect to x, it says it's 12, minus 8. This is also what we computed down here. Partial derivative of f with respect to w1 is the matrix 20, minus 16, 10, minus 8. This is what we had down here. With respect to w2 is a 25, 16. That's what we have over here. With respect to b1, it's 10, minus 8. That's what we have over here. With respect to b2, it's just 1. That's what we had there. With respect to a, it's 10, minus 8. That's what we had down here. With respect to b, it's 10, minus 8. That's what we had up here. With respect to C, it's 1 comma minus 1. That's what we had here. With respect to D, it's 1. And with respect to E, it's 1. Right. So it seems that at least we carried out these steps correctly when we went through it. Okay, so that's it for how to run the backpropagation algorithm on a feed-forward fully connected neural net. You can just execute these steps. And I think the easiest thing, if you want to do it, is to remember those rules at the end with how to handle these special types of nodes. Just remember them by heart or look them up, and then you can do the steps. Or otherwise, of course, use a library.